last time we defined the binomial coefficients that count the number of n-bit sequences with k1s, or equivalently the number of k-element subsets of a set of size n. And in this video, we want to talk about a few examples of the binomial coefficients. So let's start. So first, as we just mentioned, we counted in the previous video, we counted the number of binary sequences of length n with k1s, but as we said, that's also the number of k-element subsets of a set of size n, and therefore, and that's because there was a one-to-one correspondence, which we have shown between these sets and n-bit sequences with k1s, and therefore, the number of k-element subsets of an n set is again n choose k, okay, which is n factorial divided by k factorial n minus k factorial. So when you select committees, of course, the first thing that you know is that you always have constraints. So for example, let's say that you want to have a committee. Again, you have 7 people, but they consist of 4 boys and 3 girls. But let's say now that you want to have 2 boys and 2 girls on the committee, how many ways can you do it? So you want to choose 2 boys and 2 girls, get again a committee of 4 out of 7. So what we need to do is we need to choose 2 out of the 4 boys, and the number of ways of doing it is 4 choose 2. 4 choose 2 is ways of doing that, and then we need to select the 2 out of the 3 girls. The number of ways of doing that is 3 choose 2, and now what we want is the 2 boys and the 2 girls. So by the product rule, it's going to be the number we need is going to be the product of these 2 numbers. Now 4 choose 2 is 4 factorial divided by 2 factorial 2 factorial. So 4 factorial is 24 divided by 4, which is 6, and 3 choose 2, as we saw, is 3. So this number is going to be 18. Okay, and of course, we'll need to resolve conflicts on the committee. So again, if we have 4 boys and 3 girls, but John and Mary refuse to serve together, how many ways can we now form a committee of 4? Then if you want a committee that includes John, then notice that what we need to do is we need to choose, we have 7 people, but we now remove John and we're removing Mary, and we have 5 people left, and we need to choose 3 out of these 5 people because we're going to add John, we'll get 4. So that's how many committees we have that include John. That's 5 choose 3, which is same as 5 choose 2, which is 5 times 4 divided by 2, which is 10. And how many committees will include Mary? Again, it's going to be the same number, because when we exclude John and Mary, we have 5 people left, and out of them, because we're including Mary, we need to choose, instead of 4, we need to choose 3. That's 5 choose 3, which is 10. And how many committees will have neither John nor Mary? Well, then we have 5 people left, and out of them we need to choose 4. So that's 5 choose 4, which is 5. And notice that these are the only types of committees we can have, because we cannot have a committee with both John and Mary. So it's either one with John or with Mary or with neither. And these sets are disjoint, because these committees here will contain John, committees here will contain Mary, committees here will contain neither. So these sets are disjoint. And therefore, by the addition rule, the total number of committees that we can have is going to be 25, right? For a different type of example, suppose that you have endpoints in the plane in general position. That means that no 3 are on the same line. How many triangles can you form by connecting 3 points? Well, then you have endpoints, and you need to choose 3 of them. It's going to be n choose 3, which is n times n minus 1 times n minus 2 divided by 6. Okay, and here's another example. How many paths can you have? So suppose we are looking at this grid here. It has height 4. So we go 1, 2, 3, 4, and has width, which is 6. 1, 2, 3, 4, 5, 6. Okay. And we ask how many paths are there from the bottom left to the top right that are shortest path, namely you don't go and come back, but all of them you either go to the right or go up. Those will be paths of shortest length. So you notice that every path from start to end, if it's shortest path, it doesn't go back, and so on, is a length 10 sequence of ups and rights with 6 rights. So we can go, for example, this one goes right, 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 right. That's 4 rights, and then we have up, 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 4 heights, 4 ups, and then 2 rights. So we have a total of 6 rights. And any path that you take from here to here will have to move to the right 6 times, and we'll have to move up 4 times. So it'll be a sequence of length n, of length 10, sorry, with 6 rights and therefore 4 ups. And how many such sequences are there? The number of paths, therefore, is 10 to 6, because we have sequence of length 10 with 6 rights, and that number is 10 to 6, which if you calculate is 210. Okay, so with that, we have described what combinations are. We found how many combinations there are and choose k, the binomial coefficient. We give a formula, which is n factorial divided k factorial, and divided again by n minus k factorial. And what we want to do next is find some properties of the binomial coefficients. So that's what we're going to do next. See you then.